Electric charge is a property that some, but not all fundamental particles in nature have. The most commonly talked about fundamentally charged particles are the electrons, which orbit the outside of the atom. These are negatively charged. There's also the protons, which reside inside the nucleus, and these are positively charged. And the neutrons inside the nucleus don't have any net charge. It turns out that all fundamentally charged particles in the universe have charges that come in integer units of the elementary charge. So if you find a particle in nature, it's going to have a charge of 1 times this number, 2 times this number, 3 times this number, and it could be positive or negative. For instance, the electron has a charge of negative 1.6 times 10 to the negative 19th coulombs, and the charge of the proton is positive 1.6 times 10 to the negative 19th coulombs. However, most atoms in the universe are electrically neutral overall, since they'll have just as many negative electrons as they do positive protons. But if an atom had too many electrons, overall that atom would be negatively charged, and if an atom had too few electrons, that atom would be overall positively charged. And something that's really important to remember is that the electric charge is always conserved for every process. In other words, the total charge initially is going to equal the total charge finally after any process. So what's an example problem involving electric charge look like? Let's say 3 identically sized metal spheres start off with the charges seen below, positive 5q, positive 3q, and negative 2q. If we touch sphere x to sphere y and separate them, and then touch sphere y to sphere z and separate them, what will be the final charge on each sphere? Well, first, when we touch x to y, the total charge has to be conserved. There's a total charge of 8q amongst them, and since they're identically sized, they'll both share the total charge, which means after they touch, they'll both have positive 4q. If one of the spheres were larger, it would gain more of the charge, but the total charge would still be conserved. And now when sphere y is touched to sphere z, the total charge amongst them at that moment would be positive 4q plus negative 2q, which is positive 2q. They would share it equally, so sphere y would have positive q and sphere z would also have positive q. So the answer here is C. Opposite charges attract and like charges repel, and what Coulomb's law does is it gives you a way to find the magnitude of the electric force between two charges. The formula for Coulomb's law says that the magnitude of the electric force between two charges, Q1 and Q2, is going to equal the electric constant K, which is 9 times 10 to the 9th, times the product of the two charges, measured in coulombs, divided by the center-to-center distance between those two charges, squared. You can't forget to square this distance, and it's got to be in meters if you want to find SI units of newtons for the force. Also, don't rely on the negative and positive signs of the charges to tell you which way the force points. Just use the fact that opposite charges attract and like charges repel, and use Coulomb's law to get the magnitude of the force. So what's an example problem involving Coulomb's law look like? Let's say two charges exert an electric force of magnitude F on each other. What would be the magnitude of the new electric force if the distance between the charges is tripled and the magnitude of one of the charges is doubled? Well, we know the formula for Coulomb's law says that the force between two charges is the electric constant times one of the charges times the other charge divided by the distance between them squared. And now once we triple the distance and double a charge, the new electric force is going to be the electric constant times one of the charges multiplied by 2 times one of the charges divided by 3 times the distance, which is squared. So I'm going to get a factor of 2 on top, and this 3 will get squared, which gives me a factor of 9 on the bottom. If I pull out those extra factors, I get that the new force is going to be 2/9 multiplied by K Q1 Q2 over D squared. But this entire quantity was just the old force F. So the new force is going to be 2/9 of the old force. The electrical current I tells you the amount of coulombs of charge that passes a point in a wire per second. So if you watch some point in a wire and you count how many coulombs of charge pass by that point per second, that would be the current. Or in equation form, we can see that the current I is going to be the amount of charge that flows past a point in a wire per time. This gives the units of I as coulombs per second, which we abbreviate as an ampere. And since charge and time aren't vectors, current is not a vector either. Something that's kind of strange is that the so-called conventional direction of current would be the direction that positive charges flow within a wire. However, positive charges don't flow within a wire. The only charges that actually flow in a wire are negative charges. But it turns out that negative charges flowing to the left is physically the same as positive charges flowing to the right. So in most physics problems, we pretend as if it were the positive charges moving. However, it's really the electrons, which are negative, that are moving within the wire. So what's an example problem involving electrical current look like? Let's say 3 amps flows within a circuit. How much charge would pass by a point in that wire during a time interval of 5 minutes? Well, we know the definition of current is the charge per time. That means the charge is going to be the amount of current multiplied by the time. So we take our current of 3 amps and we multiply by the time, but we can't multiply by 5 because that's in units of minutes. Since amps is coulombs per second, we've got to convert 5 minutes into seconds, which would be 5 minutes multiplied by 60 seconds per minute, which would give us a total amount of charge of 900 coulombs. The resistance of a circuit element measures how much that element will restrict the flow of current. The larger the resistance, the less current that will be allowed to flow. And the definition of a resistance is given by Ohm's law. Ohm's law states that the amount of current that you'll get through a portion of a circuit is going to be proportional to the voltage across that portion divided by the resistance of that portion of the circuit. So between these 2 points, the amount of current that will flow is going to be equal to the voltage between those 2 points divided by the resistance between those 2 points. So the larger the resistance, the less current will flow, but the greater the voltage supplied, the greater the current will be. And this is what Ohm's law says. Even though Ohm's law gives you a way to define the resistance, you can determine the resistance of a circuit element by knowing the size and shape of that circuit element. In other words, the resistance of a cylindrical resistor is going to be equal to the resistivity, which is a measure of an object's natural resistance to current, multiplied by the length of that resistor. The longer the resistor, the greater the resistance and the more it will resist the flow of current. And then divided by the cross-sectional area of that resistor, which would be this area right here that current is either flowing into or out of. If the resistor is cylindrical, the area of this circle would be pi times r squared, where little r would be the radius of this cross-sectional area. The units of resistance is ohms, and it is not a vector. It is always positive or zero. So what's an example problem involving Ohm's law or the resistance of a cylindrical resistor look like? Let's say a battery of voltage V is hooked up to a single cylindrical resistor of length L and radius little r. And when that's done, a current I is flowing through the battery. What is the resistivity rho of that resistor? Well, we know Ohm's law states that the current that flows through a portion of a circuit will be equal to the voltage across that portion divided by the resistance of that portion. And this means the resistance of this resistor is going to be the voltage of the battery divided by the current. To factor resistivity into this, we have to use the formula for the resistance of a cylindrical resistor, which is rho times L over A. This gives us the resistance of the resistor, which has got to equal V over I. And now we can solve for the resistivity rho. We get V times A over IL. But since we're given the radius little r, we've got to write the area in terms of that radius. So this is going to be V times pi r squared divided by I times L, which gives us an answer of C. When dealing with complicated circuits with many resistors, you often have to reduce those resistors into smaller equivalent amounts of resistors. And the 2 ways you do this are by finding 2 resistors that are in series or in parallel. Resistors will be in series if the same current that flows through the first resistor flows through the next resistor. If the current branched off in between them, these resistors would no longer be in series. But if they're in series, you can find the equivalent resistance of this section of wire by just adding up the 2 individual resistances. So the current for resistors in series must be the same, but the voltage might be different, since they could have different resistances. 2 resistors will be in parallel if a current comes in, splits into 2 parts, goes through 1 resistor each, and then rejoins before hitting anything else in the circuit. And if this is the case, you can find the equivalent resistance of this portion of the circuit, i.e. between these 2 points, by saying that 1 over the equivalent resistance is going to equal 1 over the resistance of the first resistor plus 1 over the resistance of the second resistor. But be careful, 1 over R1 plus 1 over R2 just gives you 1 over R equivalent. If you want R equivalent, you're going to have to take 1 over this entire side in order to get R equivalent. So what's an example problem involving resistors in series and parallel look like? Let's say we have the circuit shown below, and we want to know what current flows through the 8 ohm resistor. Now you might be tempted to say that since Ohm's law says that the current is delta V over R, we can just plug in the voltage of the battery, which is 24 volts, divided by the resistance of the resistor, which is 8 ohms, and that would give us 3 amps. But that's not right at all. When using Ohm's law, the current that flows through a resistor, R, is going to be equal to the voltage across that resistor divided by the resistance of that resistor. So if we plug 8 ohms into the denominator, we've got to plug in the voltage across that 8 ohm resistor. But the voltage across the 8 ohm resistor is not going to be the full 24 volts of the battery. It's going to be less than 24 volts. In other words, the battery provides a voltage between this point and this point of 24 volts, but there's going to be voltage drops across the 6 and 12 ohm resistors, which make it so that the voltage across the 8 ohm resistor is not going to be the full 24 volts. So we have to reduce these resistors to a single resistance. The 6 and the 12 are in parallel, so we can say that 1 over 6 plus 1 over 12 would equal 1 over the resistance of that portion of the circuit. This is going to equal 3/12, which is 1/4. So that means that parallel portion of the circuit has an equivalent resistance of 4 ohms. So between this point and this point, there are 4 ohms of resistance, and that equivalent resistance is in series with this 8 ohm resistor. So we can add 4 and 8 and get 12 ohms of total resistance. And now I can say that the full 24 volts of the battery is applied across this entire equivalent resistance of 12 ohms. So if I come up here and change this 8 ohms to 12 ohms of equivalent resistance for the total circuit, I'll get the correct current that flows through the battery of 2 amps. And since that's the current that's flowing through the battery, that had to be the current that's flowing through the 8 ohm resistor as well, since this 8 ohm resistor and the battery are in series. Elements in a circuit often use electrical power. That is to say, when current runs through a resistor, the electrons moving through that resistor turn some of their electrical potential energy into energies like heat, light, or sound. And the rate at which these electrons are turning their energy into other forms of energy is called the electrical power. So the rate at which a resistor is turning electrical potential energy into heat is the electrical power used by that resistor. In other words, the amount of energy converted into heat divided by the time it took to convert that energy is the definition of the power. And there's a way to determine this number of joules per second in terms of quantities like the current, the voltage, and the resistance. The power used by a resistor can be written as the current through that resistor multiplied by the voltage across that resistor. Or if you substituted Ohm's law into this formula, you'd see that this is equivalent to the current through that resistor squared multiplied by the resistance of the resistor. Or you could rearrange these formulas to get that the power used by a resistor would also be the voltage across that resistor squared divided by the resistance of that resistor. All three of these, if used correctly, will give you the same number for the power used by a resistor. And if you wanted to determine the number of joules of heat energy converted, you could set any one of these equal to the amount of energy per time and solve for that energy. The units of electrical power are the same as the regular units of power, which is watts, i.e. joules per second, and electrical power is not a vector. So what's an example problem involving electrical power look like? Let's say a light bulb of resistance R is hooked up to a source of voltage V, and a second light bulb of resistance 2R is hooked up to a source of voltage 2V. How does the power used by the second light bulb compare to the power used by the first light bulb? Since we have information about R and V, I'll use the version of the power formula that says that the power used by a resistor is going to be delta V squared over R. So in terms of quantities given, the power used by the first light bulb is going to be V squared over R. And the power used by the second light bulb is going to be equal to the voltage across the second light bulb, which is 2 times the voltage across the first light bulb, and we square that, divided by the resistance of the second light bulb, which is going to be 2 times the resistance of the first light bulb. The 2 squared on top is going to give me a factor of 4, and I'll have another factor of 2 on the bottom. So if I factor out this 4 divided by 2, I get that the power used by the second light bulb is going to be 2 times V squared over R, but V squared over R was the power used by the first light bulb. So the power used by the second light bulb is going to be 2 times the power used by the first light bulb, and so the light bulb of resistance 2R has twice the power. And that means it'll be brighter. The quantity that determines the brightness of a light bulb is the electrical power of that light bulb. It's not necessarily the resistance or the voltage, it's the combination of the two in this formula that will tell you the electrical power and therefore the brightness of the light bulb. Two of the most useful ideas in circuits are referred to as Kirchhoff's rules. The first rule is called the junction rule, and it states that all the current entering a junction must equal all the current exiting that junction. In other words, if you add all the current that flows into a junction, that has to equal all the current that flows out of that junction, because current is just flowing charge and charge is conserved. So charge can't be created or destroyed at any point in this circuit. No more than water can get created or destroyed within a series of pipes. And the second rule is called the loop rule, which states that if you add up all the changes in electrical potential, i.e. voltages, around any closed loop in a circuit, it'll always add up to zero. So if you add up all the voltages encountered through a closed loop through a circuit, it always adds up to zero. And this is just a result of conservation of energy. The electrons will gain energy when they flow through the battery, and they'll lose energy every time they flow through a resistor. But the total amount of energy they gain from the battery has to be equal to the total amount of energy they lose due to the resistors. In other words, if we consider a complicated circuit that has a battery and 3 resistors, the total current flowing into a junction, I1, would have to be equal to the total current coming out of that junction, I2 and I3, since no charge gets created or destroyed. And that means when these two currents combine again, the total current flowing out of that section is going to again be I1. And if we follow a closed loop through this circuit, the sum of all the voltages around that loop have to add up to zero, i.e. the voltage of the battery minus the voltage drop across the first resistor minus the voltage drop across the second resistor would have to equal zero. So what's an example problem involving Kirchhoff's rules look like? Let's say we had the circuit below and we wanted to determine the voltage across the 6 ohm resistor. To do this, we could use the loop rule. I'll start behind the battery and I'll go through the resistor I want to determine the voltage across. I'll add up all the voltages across that loop and set it equal to zero. So the voltage across the battery is going to be positive 24 volts minus the voltage across the 6 ohm resistor, and then minus the voltage across the 8 ohm resistor has to equal zero. But we're given this current, so we know that 2 amps flows through the 8 ohm resistor. And you can always determine the voltage across a resistor using Ohm's law. So the voltage across the 8 ohm resistor is going to be 2 amps, which is flowing through the 8 ohm resistor, multiplied by 8 ohms, and we get 16 volts, which I can plug into here. And this gives me 24 volts minus the voltage across the 6 ohm resistor minus 16 has to equal zero. And if I solve this for the voltage across the 6 ohm resistor, I get 24 volts minus 16 volts, which is 8 volts. So the voltage across the 6 ohm resistor would be 8 volts. Note, because the 12 ohm resistor and the 6 ohm resistor are in parallel, the voltage across the 12 ohm resistor would also be 8 volts, because the voltage across any two elements in parallel have to be the same. Voltmeters are the device that you use to measure the voltage between 2 points in a circuit. When hooking up a voltmeter, you've got to hook it up in parallel between the 2 points you want to find the voltage across. In other words, to determine the voltage between this point and this point, which would be the voltage across R3, you would hook up the voltmeter in parallel with R3. Ammeters are the devices we use to measure the electrical current that passed through a point in a circuit, and ammeters have to be hooked up in series with the circuit element you want to determine the current through. In other words, if we wanted to determine the current through R1, we would hook up the ammeter in series with R1. Note that for these electrical devices to work well, the ammeter should have almost zero internal resistance, thereby not affecting the current that flows through the circuit. And voltmeters should have near infinite resistance, so that it doesn't draw any of the current from the resistor. In reality, ammeters have a very small but non-zero internal resistance, and voltmeters have a very high but not infinite internal resistance. So what would an example problem involving voltmeters and ammeters look like? Let's say we had the circuit shown below, and these numbered circles represent possible places we could stick a voltmeter to measure the voltage across the 8 ohm resistor. Which two of these voltmeters would correctly give the voltage across the 8 ohm resistor? And you have to be careful. Some AP problems are going to require you to select 2 correct answers for the multiple choice, so be sure to read the instructions carefully. Voltmeter number 4 is a terrible choice. You never hook up your voltmeter in series with the circuit element you're trying to find the voltage across. And voltmeter number 1 is doing nothing really, because it's measuring the voltage between 2 points in a wire with nothing in between that wire. So the voltage measured by voltmeter 1 should just be 0, since the voltage across a wire of 0 resistance should just give you 0 volts. So the correct choices would be voltmeter number 2, which gives you the voltage across the 8 ohm resistor, and voltmeter number 3, which also gives you an equivalent measurement of the voltage across the resistor 8 ohms.